Welcome to the Linear Independence lecture in the series, The Shape of Space Linear Algebra. If you recall from the last lecture, I talked about spanning sets and I asked the question about when do you have a minimum spanning set, minimum in the sense of having the least number of vectors that span a given subset or an entire vector space. And that's questions very much related to the concept of linear independence, which we're going to talk about in this lecture. Let's start with the definition of linearly independent. In a given vector space, a set of vectors is said to be linearly independent if none of its elements is a linear combination of the other elements in the set. Otherwise, we say the set is linearly dependent. So let's look at a couple examples. If we take the vectors 1, 0, and 0, 1, they're independent because there's no way of writing this vector in terms of the other. They have a 0 in different positions here. And so these are independent. On the other hand, these three vectors, 1, 0, 0, 0, 1, 0, and 2, 2, 0, are dependent because we can write the vector 2, 2, 0 as 2 times the first vector plus 2 times the second. We have a theorem that we'll be using as we progress through this lesson. Given a subset S of a vector space V and some vector small v in the vector space, the span of S union V, in other words, if you add the vector V to S, equals the span of S if and only if V is an element of S. So going in the reverse direction here, if we assume V is an element of S, then of course S union V is just equal to S, and then clearly the span of these two things that are equal is the same. So going in the other direction, assume the span of S union V equals the span of S, and let S equal this set here, S sub 1, S sub 2 up to S sub n. Clearly V is an element of the span of S union V, which we're told is equal to the span of S. That's our assumption. So we can write, that implies that we can write V is a linear combination of the vectors in S. So I've shown that here, where these A sub I are all real numbers. They're the coefficients. And if we assume V is not an element of S, then V is a linear combination of elements of S, but is not itself in S. However, if V were not in S, then adding V to S would imply that the span of S union V has a larger span than the span of S, contradicting our assumption that the span of S union V equals the span of S. So that means that V has to be in S. From our theorem on the previous slide, we have this theorem number 6. We're given that a vector V in a subset S of a vector space V, and the theorem says that the span of S equals the span of S with V removed from it, if and only if V is linearly dependent on the other S vectors of S. So in other words, if you can write V as a linear combination of the other vectors in S, then removing it doesn't decrease the span of S. That seems almost evident, self-evident. The next theorem gives us another way of checking whether or not we have an independent set of vectors, and it says that a set of vectors S is linearly independent if and only if the equation here, A1, S1, A2, S2, added all the way up to A and Sn equals 0, implies that all the coefficients are equal to 0. So first we'll assume that the set S is not linearly independent, and in other words, S is dependent, which means there's some Si that can be written as a linear combination of the other vectors. So I'm showing that here. And then we can just move the Si inside of this to the right, and we basically have a linear combination of the vectors from S that equals 0, where one of them, this one, at least one of them, has a coefficient not equal to 0. So in other words, it negates this part of the theorem. Then we can go in the other direction and assume that S is linearly independent. Then by definition, no vector S sub I of S is a linear combination of the other vectors in S. Thus, there can be no linear relationship among the vectors in S where some of the coefficients have non-zero values, and that's the that implies this here, that all of the coefficients are 0 in that case. We can use the previous theorem to determine whether or not a set of vectors is linearly independent, and we have an example of that here. We have three vectors, 1, 2, 3, 4, 7, 2, 9, 3, 1. And so what we want to show is that if we take a linear combination, as I have here, and it's equal to 0, then the coefficients x1, x2, x3 must be equal to 0. So the way we do that is we write this out. We have x1 times 1 plus x2 times 4 plus x9 times x3 equals 0. And then we go to the second components here. We get this equation, and then the third component, we get this equation here. So we can write this as a matrix equation, AX equals 0. A is just the 1, 4, 9, 2, 7, 3, 3, 2, 1. Then X is the X1, X2, X3. And of course 0 is the right-hand side here. So we want to solve this equation. If we can determine that this has a unique solution, then we've proven that these three vectors are independent. We'll continue on the next slide. As I mentioned, if the inverse of A exists, then we have a unique solution, x equals 0, to our matrix equation. And this would imply that the given vectors are linearly independent. And in fact, the inverse of A does exist. It's this expression here. You can check it a few ways or do it a few ways. I used Wolfram Alpha. If you put in the command inverse, then this is how you enter the matrix. This is the first row, the second row, the third row. Then you get this back. You can also use a program, a package called Julia from MIT. This is the link to it. And you download that and install it on your computer, and it has an enormous amount of capability. And one of the capabilities it has is to take inverses. So we enter the matrix like this here with semicolons separating the rows, and then we just do the command A to the -1 power, and it gives you the inverse. As far as I could tell, Julia always works with floating decimals here like we have, rather than the fractions. But I did check a few of these. I divided 124 into 1, and I got this number, and I checked another one or two of them, and these are the same, which I would have expected. Okay, so we've shown here that we have three linearly independent vectors. In our second example, we actually have dependent vectors. So this 1, 2, 3, 7, 9, 2, 8, 11, 5 turns out to be dependent. And what we can start in the same way that we started in the example 1, basically assuming that they are linearly independent. We set up this equation here. Linear combination of the 3 equals 0. We can write that as a system of equations. And if we can also write that as a matrix equation where A is 1, 7, 8, 2, 9, 11, 3, 2, 5. It turns out A inverse does not exist. So we know that that implies that there's not a unique solution to the system. And we can go ahead and actually find an infinite number of solutions by putting this system of equations into a matrix and then doing the Gaussian elimination. So we take twice the first row from the second, 3 times the first row from the third, and we get this. We can divide the second row by 5 and get 1, 1, 0. And then you can take 19 times this and add it to this row here, and it eliminates this row. And then you can subtract 7 times the second row from the first, and you get this form here. Let's continue on the next slide. I copied the last matrix we had on the previous slide here for our reference, and then this basically says that x sub 1 plus x sub 3 equals 0, which we can write as x sub 1 equals minus x sub 3, and then this one here says x sub 2 plus x sub 3 equals 0, which we can write as x sub 2 equals minus x sub 3. Then if we take the vector x sub 1, x sub 2, x sub 3, and we substitute these values in, we get this here. And we can factor out an x sub 3. And basically we've determined that our initial systems of equations have an infinite number of solutions, all multiples of the vector minus 1, minus 1, 1. And that non-zero solutions, I should emphasize, and so that means the initial set of vectors is linearly dependent, and that solves our problem, or gives us the answer to our problem. And we could do it another way. We can find the span of these 3 vectors in R3, and if it's actually something less than R3, then there needs to be a dependency between these 3 vectors. So we do that by putting the 3 vectors into a matrix and then noting that we can do row operations, and that does not affect the span. So we do that here. We take 7 times the first row from the second, and then 8 times the first row from the third. We get this here. We divide by minus 5 into the second row. Then we can also eliminate the third row because these are exactly the same, so we can subtract one from the other. We could take twice the second row from the first and get this here. And so basically this is these 2 vectors span a 2-dimensional space, which is less than all of R3. So these 3 vectors here must be dependent, and that's a second way of proving dependency between the vectors. We have a few more examples here. Example number 3, in any vector space, any subset containing the 0 vector is dependent. So for example, the subset 0, 0, 0, 1, 0, 0 in the vector space R3, we can write 0, 0, 0 equals 0 times 1, 0, 0, and thus the 2 vectors are linearly dependent. And then example 4, the empty set of a vector space is linearly independent since there is no non-trivial linear relationship among its members, of which there are none. So this is what's called vacuously fulfilling a requirement. But this comes up in some proofs, so I'll just mention it here. So as a convention, we define the sum of zero many vectors, so in other words no vectors, to be the zero vector. This seems odd, but will be needed in some of the following discussions. So you may want to just take note of this unusual convention. The following theorem states that a spanning set is minimal if and only if it is linearly independent. In particular, we have theorem 8. A set S is linearly independent if and only if, for any vector v, an element of S, its removal shrinks the span. In other words, the span of S with v removed is a proper subset of span S. Proper meaning it can't possibly be equal to. That's a standard notation here. When you put a little line underneath the subset, that means it's possible for the subset to equal the containing set. So this is if and only if. We need to prove it in both directions. If S is linearly independent and we remove some vector v, then there is no way to represent v with the remaining vectors in S. Thus, the span of S with v removed is a proper subset of span S. And going the other way, if S is linearly dependent, then there is some vector v, an element of S, such that v is a linear combination of the other vectors in S. So if we remove v, we have that the span of S minus v equals the span of S. The following theorem concerns adding a vector to a set, so it's sort of in contrast to the previous theorem. Given a linearly independent set S in a vector space V and a vector V not in S, the set S union V is linearly independent if and only if V is not an element of the span of S. So the theorem is equivalent to the following. This is sort of the negation of it, but we're going to prove this version of the theorem. The set S union V is linearly dependent if and only if V is an element of the span of S. So if V is an element of the span of S, then clearly S union V is linearly dependent, right? You're just adding an element that we know can be written in terms of the other vectors. So this set here is dependent. Going the other way, this is a little bit more involved, assume S union V is linearly dependent. This implies there's a linear relationship among the elements of S union V, with one or more of the coefficients being non-zero. So we have this relationship here. If A, and then we have a couple of cases. So if A equals 0, then at least one of the A sub I equals 0, but that implies S is linearly dependent. It's a contradiction. And thus A does not equal 0. So we can rewrite the above just subtracting AB from both sides and then dividing by A. We get V is a linear combination of the vectors from S, which implies that V is an element of the span of S. We have one last theorem for this lesson. I think it's kind of obvious, and I'll leave it as an exercise for you to think through, but let's just read it here. A subset of a linearly independent set is also linearly independent. So if you can't write the vectors in the set in terms of each other, and you remove one, then of course you would expect to still have that condition. And then going the other way around, a superset, in other words, adding to of a linearly dependent set is also linearly dependent. So if you could write one vector in terms of the other vectors, and then you add yet another vector, you're still going to have this dependency. So kind of giving you the proof, or at least kind of wave my hand through the proof here. So just another theorem to keep in mind. Now we're going to put together some of these ideas from the last two lessons in the next lesson. We'll talk about something called a basis, where you have both spanning set and linear independence, and that'll give you what's called a basis for a vector space. We'll talk about that in the next lesson.